Chapter 15. Correlational Research. Introduction. In correlational research, researchers investigate possible relationships among variables without trying to influence those variables. Correlational studies cannot determine the causes of relationships among variables. However, they often provide the basis for future experimental studies. This chapter discusses the nature of correlational research, provides several examples of correlational studies, and describes some of the problems involved in conducting such research. The nature of correlational research. The major characteristic of correlational research is seeking out associations among variables. 2. Purposes of correlational research. Correlational studies are carried out either to help explain important human behaviors or to predict likely outcomes. A. Explanatory studies. A major purpose of correlational research is to clarify people's understanding of important phenomena by identifying relationships among variables. B. Prediction studies. If a relationship of sufficient magnitude exists between two variables, it becomes possible to predict a score on one variable if a score on the other variable is known. The variable that is used to make the prediction is called the predictor variable. The variable about which the prediction is made is called the criterion variable. Both scatter plots and regression lines are used in correlational studies to predict a score on a criterion variable. A predicted score is never exact. As a result, researchers calculate an index of prediction error, which is known as the standard error of estimate. C. More complex correlational techniques. Multiple regression is a technique that enables a researcher to determine a correlation between a criterion variable and the best combination of two or more predictor variables. The coefficient of multiple correlation, R, indicates the strength of the correlation between the combination of the predictor variables and the criterion variable. The value of a prediction equation depends on whether it predicts successfully with a new group of individuals. When the criterion variable is categorical rather than quantitative, discriminate function analysis, rather than multiple regression, must be used. Factor analysis is a technique that allows a researcher to determine whether many variables can be described by a few factors. Path analysis is a technique used to test the likelihood of causal connections among three or more variables. 3. Basic steps in correlational research. These include, as in most research, selecting a problem, choosing a sample, selecting or developing instruments, determining procedures, collecting and analyzing data, and interpreting results. A. Problem selection. The following three major types of problems are the focus of correlational studies. Is variable X related to variable Y? How well does variable P predict variable C? What are the relationships among a large number of variables, and what predictions can be made that are based on them? B. Sample. The first step in selecting a sample is to identify an appropriate population, one that is meaningful and from which data on each of the variables of interest can be collected. The minimum acceptable sample size for a correlational study is considered by most researchers to be no less than 30. C. Instruments. The instruments used to measure the two, or more, variables involved in a correlational study may take any one of a number of forms, but they must yield quantitative data. Although data sometimes can be collected from records of one sort or another, e.g., grade transcripts, most correlational studies involve the administration of some type of instrument, tests, questionnaires, and so on, and sometimes observation. Instruments must show evidence of validity and reliability. D. Design and procedures. The basic design used in a correlational study is quite straightforward. 2, or more, scores are obtained from each individual in the sample, one score for each variable of interest. The pairs of scores are then correlated, and the resulting correlation coefficient indicates the degree of relationship between the variables. E. Data collection. In an explanatory study, all the data on both variables will usually be collected within a fairly short time. In a prediction study, the measurement of the criterion variables often takes place sometime after the measurement of the predictor variables. F. Data analysis and interpretation. When variables are correlated, a correlation coefficient is produced. The closer the coefficient is to plus 1.00 or 1.00, the stronger the relationship. Coefficients that are at or near 0.00 indicate that no relationship exists between the variables involved. 4. What do correlation coefficients tell us? The meaning of a given correlation coefficient depends on how it is applied. Correlation coefficients below 0.35 show only a slight relationship between variables. Correlations between 0.40 and 0.60 may have theoretical and or practical value depending on the context. Only when a correlation of 0.65 or higher is obtained can reasonably accurate predictions be made. Correlations over 0.85 indicate a very strong relationship between the variables correlated. V. Threats to internal validity in correlational research. Threats to the internal validity of correlational studies include subject characteristics, location, instrument decay, data collection, testing, and mortality. Results of correlational studies must always be interpreted with caution, because they may suggest, but they cannot establish, causation. A. Subject characteristics. Whenever two or more characteristics of individuals, or groups, are correlated, there exists the possibility that yet other characteristics can explain any relationships that are found. In such cases, the other characteristics can be controlled through a statistical technique known as partial correlation. B. Location. A location threat is possible whenever all instruments are administered to each subject at a specified location, but the location is different for different subjects. If both measures are not administered to all subjects under the same conditions, the conditions rather than the variables being studied may account for the relationship. C. Instrumentation. In any study using a particular instrument many times, thought must be given to the possibility of instrument decay. When both variables are measured by an observational device at the same time, care must be taken to ensure that observers don't become tired, bored, or inattentive. This may require using additional observers. Characteristics of data collectors can create a threat if different persons administer both instruments. Gender, age, or ethnicity, for example, may affect specific responses, particularly with opinion or attitudinal instruments, as well as the seriousness with which respondents answer certain questions. Another instrumentation threat can result from unconscious bias on the part of the data gatherers whenever both instruments are given or scored by the same person. It is likely that the observed or scored performance on the first test will affect the way in which the second test is administered and or scored. D. Testing. The experience of responding to the first instrument that is administered in a correlational study may influence subject responses to the second instrument. The solution is to administer instruments, if possible, at different times and in different contexts. E. Mortality. Mortality, strictly speaking, is not a problem of internal validity in correlational studies since anyone lost must be excluded from the study. Correlations cannot be obtained unless a researcher has a score for each person on both of the variables being measured. There are times, however, when loss of subjects may make a relationship more, or less, likely in the remaining data, thus creating a threat to external validity. Oh, this is because the sample actually studied is often not the sample initially selected, because of mortality. 6. Evaluating threats to internal validity in correlational studies. Step 1, ask, what are the specific factors that are known to affect or could logically affect one of the variables being correlated? Oh, it does not matter which variable is selected. Step 2, ask, what is the likelihood of each of these factors also affecting the other variable being correlated with the first? Oh, a factor must be related to both variables to be a threat. Step 3, evaluate the various threats in terms of their likelihood, and plan to control them. Oh, if a given threat cannot be controlled, this should be acknowledged and discussed.